Ice cores are incredibly valuable tools that help us to see into the past and learn how Earth's climate has changed over time. The ice core records go back many hundreds of thousands of years. If we look at ice cores collected from Greenland, we can look back about 110,000 years, and these ice cores are about 2 miles long, or if you're drilling down into the ground, you can think of them as 2 miles deep. In Antarctica, we've been able to drill ice cores that go back 750,000 years. Scientists can also compare the findings from Antarctica and Greenland with other ice cores that they're able to get out of glaciers in the Andes Mountains and the Himalaya Mountains, and so they can cross-check their findings. Ice cores work very similarly to ocean cores in that they provide a vertical timeline and give us evidence as you go down through the record of climates in the past, with the data from the bottom of the core being the oldest. So some of the pictures here, this shows drilling in the Greenland ice cap in the summer of 2005, and these ice cores have now been studied in great detail. So what do these ice cores tell us? They tell us a lot of different things. It's amazing to me how much information you can get out of ice. But one thing they can tell us the temperature over time. And so we think of ice as all being the same temperature. It's all cold, it's all frozen. But if you look at the temperature of the ice core as they extracted the core from the ice sheet, you can see that the temperature in the middle of the ice core remained about the same as it was when that ice was deposited. And so we can see when there were ice ages in the core based on colder temperatures, then interglacial periods when there were not ice ages, and then again another ice age here. As you get towards the bottom of the core, there's friction as that ice travels along bedrock, and so you can get warming in that ice, and so the temperature increases. Also, our current surface temperature is warmer than it has been in many past ages, and so you can see there's warming near the surface of the ice core. Also, when they extract that ice core, it looks different depending on the age and how long it's been deposited. So the relatively young shallow snow that's at the top of the core, it looks like coarse granule crystals in the ice core. These are called firn. The older, deeper snow gets compacted further, and you can see in there each year is a different line in the core, and you can see it looks kind of striated. And then when you get to the bottom of the core, the glacier starts to pick up rocks and sand and silt from underneath, from that bedrock area at the bottom of the glacier, and it can turn it kind of brownish. So you still see the layers, but they have some brown silt mixed in. Scientists also, in these ice cores, they can look at tiny particles that get trapped in the snow when that snow fell onto the ice sheets. So they look at things like dust, volcanic ash, smoke, little smoke particles get deposited, pollen, and all of these help them to learn about the climate at the time. So if there's volcanic ash, for example, you know that a volcano erupted, and volcanoes do impact climate. They can also look at gas bubbles that are trapped in the ice, and that helps them to learn about the amount of carbon dioxide, for example, or methane gas that was in the atmosphere at the time, and so they can correlate those with past temperatures and climates. Okay, so another piece of information we get from ice cores is the oxygen balance that's in the ice. And so as we travel through the depth of the ice core, we look at the oxygen isotope ratios, and these tell us a lot about climates in the past. So if you'll remember back to your chemistry from high school or possibly college, you'll remember oxygen atoms have 3 different isotopes that are commonly known, and these isotopes have 8, 9, or 10 neutrons in the nucleus of the oxygen atom. And so oxygen that's in water, water molecules that have oxygen 16 in them, these are the lightest water molecules, and so they will evaporate from the ocean first, and they will travel the furthest in the atmosphere before they get deposited back down, or they fall down when the air cools and condenses. Water molecules that have oxygen 18 in them, these molecules are heavier, and they will condense first, and they'll condense at cooler temperatures. And so they don't travel as far from the equator because that air is cooler and it condenses earlier. Okay, so paleoclimatologists, these are people climatologists that study climates of the past. They use oxygen ratios from water that gets trapped in the glaciers, as well as oxygen that's absorbed in the shells of marine plants and animals and also deposited, to measure past temperatures and rainfall. And so these polar ice cores help us to figure out what the climate was at different stages and different periods of time. So the take-home message is when there's less heavy oxygen, that means temperatures were cooler. So because the oxygen 16 traveled farther and was deposited farther away.